So let's take a look at a couple of the problems that we'll be doing on this week's homework. Since we missed class yesterday, this will be just a little bit of a catch-up for those that want to get started before we discuss this in lecture on Friday. Now, the first two really take a look at using Xfoil to calculate transition locations. So let's go to Xfoil really quickly and just pull this up as an example to get a feel for what this is going to look like. So I'm going to load up a NACA 0012 and go to the operations menu, and let's just look at it first in terms of the inviscid flow over the airfoil. And so this is at 0 angle of attack, and this is what it's going to look like at 5 degrees angle of attack. So note the suction surface pressure distribution and the pressure surface pressure distribution. Now, obviously, for transition from laminar flow to turbulent flow, you have to have viscous effects turned on. You can think of this in an inviscid flow as essentially always being laminar. Now, interestingly enough, in most calculations where we're going to make assumptions about what the flow looks like, for high Reynolds number applications, we can usually get a good estimate of that by looking at purely inviscid flow. Many of the aircraft we fly today, where those airfoils were initially defined using inviscid flow assumptions. You think, hell, wait, no viscosity. That means we're going to have a laminar flow solution. We think about this in terms of the thickness of the boundary layer. At really, really high Reynolds number flows, your boundary layers are going to be very, very small. We can see an example of this if we go to viscosity, turn viscosity on. Let's start with something small, say 50,000, and go back to this alpha of 5 degrees. And you can see your boundary layer here. You can see it's relatively thick and relative, it's still very small. Relative in this sense means in relation to the chord length. You can also see where the flow is transitioning at. So note our laminar separation bubble here. So as our flow goes from laminar flow, we have a small separation region, and then that forces transition naturally by generating that laminar separation bubble. So we go from laminar flow to turbulent flow. Now I have to be careful on how we say forced, because this is the flow itself imposing transition from laminar to turbulent flow on the boundary layer. Typically when we say forced, we're going to mean that we are doing that ourselves, and we'll look at an example of how to do that. Now if I go back and change Reynolds number and let's look at our critical Reynolds number case of 500,000. Now keep in mind that when we're putting Reynolds number in here, this is the Reynolds number based upon the chord length of our airfoil. Okay. When we say critical Reynolds number, so I have an RE sub C, that is going to tell you the location or the value of Reynolds number at which the flow transitions naturally on its own from laminar to turbulent flow. So if we go back to this airfoil, and let's just look at alpha of 0, you'll notice here that transition is kind of late stage at this angle, at this particular Reynolds number in this angle of attack. So it's occurring around that 0.8 C location. So this is for that overall Reynolds number of 500,000. From this, we could look at it and determine what that REC value is by looking at the location of where this transition point is happening at. So in this case, this is going to be somewhere around 400,000 for this particular condition. So slightly lower than our REC value of 500,000. Now for this particular problem, we're using this 500,000 and we're looking at it as a RE over length scale formulation, and that's very typical of how we tend to think of these in tests, because as we take an airfoil from the wind tunnel and put on a full-scale aircraft, we want to vary that length, so we run our calculations for boundary layer measurements as a function of RE divided by that length scale. So this where let's say we stick with that 100 feet per second flow velocity. If this were a 1 foot airfoil, then that transition location, we run that calculation for a critical Reynolds number of 500,000, is going to be around 3/4 of a foot, give or take, and you can run the detailed numbers on that. If you scale or take a larger airfoil, let's say 10 feet, for that same critical Reynolds number of 500,000, it's still going to be 3/4 of a foot, because that REC is telling you where that flow is transitioning at. Now, the overall Reynolds number of that airfoil obviously is going to be much larger. So whenever we're putting Reynolds number values in here into Xfoil, and let's say we could do 5 million, same alpha, you'll notice you don't even see the translation location on this airfoil because it's so far up near the leading edge. So keep that in mind as you're playing around with these values of overall Reynolds number and critical Reynolds number. Now, what we can do in this operation menu is take a look at the boundary layer parameters. So if you come in here and go down to the VPAR menu, it allows you to edit certain boundary layer parameters. So first off, let's go back to Reynolds number of 500,000 again for this particular airfoil. And we can see where that transition location is at. Let's look at an angle attack of 5 degrees. Notice it's moved up closer to the leading edge of the airfoil. Let's look at something slightly lower, somewhere in between. So we can still easily spot where this natural transition is happening at. In this case, it's around, say, the 0.65 mark on this particular airfoil. We want to be able to look at the impact of actually modifying that, and that's what the options in the boundary layer submenu allow us to do. You'll notice there are lots of different options here in terms of the boundary layer formulation. Notice something like the critical amplification exponent or incrit. This value is essentially a measure of your free stream turbulence intensity that you have within the flow. If you're flying within very clean air or if you're flying in dirty air. Typically flying in an ambient environment is going to give you a much cleaner flow with a lower level of turbulence unless you're flying into, for example, clear air turbulence or very windy, gusty conditions, while a clean wind tunnel is going to have slightly higher turbulence intensity than a dirty wind tunnel like ours, for example, is going to have a higher turbulence intensity than that. And that's going to have a big impact on where that natural transition is going to happen at. Now, what we're going to look at is this trip location. And before I do that, I'm going to go back and do a quick polar for this particular situation. So let's turn our polar accumulation on. We're not going to save the data. And I'm just going to do a sequence, in this case, since it's a symmetric airfoil, from 0 to 12 in increments of 1 degree. And we have this plot over here for our transition locations. And you can tell which one is which based upon what's happening with the angle of attack or your drag polar here on this side, because as we go back to the flow, and I'm going to turn this back off so I'm not accumulating the polars in this case. You can see where these transitions are occurring at. And actually I'm going to make sure I turn my iteration values up here so I can get a much cleaner flow in this case. And so you can see your transition locations are actually moving upstream as you're going to higher angles of attack because of the increase in your adverse pressure gradient acting on the flow. And that has a very large impact on how your boundary layer is evolving. So let's go back to this VPAR menu again, and you have this option of changing the location of the trip. And so what we're going to do is just move it pretty far forward upstream. So let's put it at 0.1 on both the upper and the lower side of the airfoil. And then we're going to go back, accumulate these polars again, and run the same sequence from 0 to 12. You'll notice in this case, oh, look, my laminar separation bubbles here have now disappeared. I don't see them in this plot like I saw before. They're all located up here because I'm actually forcing the flow to transition from laminar to turbulent flow at this particular location. In most cases, for these angles of attack that I ran, my flow is still laminar here. Now, it may transition before, and in that case, for Xfoil, our trip does no good. Xfoil essentially ignores it because your flow is already transitioned from that laminar boundary layer to that turbulent boundary layer. But if it has not, at a lower angle of attack, then your flow is going to be forced to automatically transition from laminar flow to turbulent flow. And that's something that we do pretty regularly on airfoils, where we want to avoid the flow from being laminar on the aft side, where we might have a predilection towards a separation or early stall. Now, in some cases, for example, sailplane airfoils, some other laminar flow airfoils, we want to try to maintain that laminar flow as much as possible, but more often than not, in practical situations, our flow is already going to be tripped by the way that our airfoil, our wing, in this case, has been manufactured. That we have, a lap joint or a slat or leading edge flap near that front surface, and that's going to force transition. So now we can go back to that polar plot, and you can see the difference. Oh, there's my transition location right here for this second case. And you can see it's fixed at that 0.1 for both the upper and the lower surface. And I could go back and change that. Let's actually do this just for grins. So I'm going to turn my polar accumulation off, go back to VPAR. Let's change the transition location to 0.25 on the top, and let's move it back to 0.5 on the bottom, just so that we'll see the difference between those two. Then I'm going to turn my polar accumulation back on, and then run through my sequence again from 0 to 12, 1 degrees angle of attack, and then go back to the plot. So here are my three cases. So I have my natural transition case right here, which, as we saw, looks like, at least for angle of attack of 0, is transitioning around 400,000, give or take. So that's a critical Reynolds number, but that critical Reynolds number is changing, at least on the upper surface, as my angle of attack is increasing. So now you can see these two cases where I have my natural transition location, the upper surface that we're really worried about here, my forced transition at 0.1C, and my forced transition at 0.25C, which you'll notice as we're increasing angle of attack, we're starting this transition from the back, and it's moving forward towards the leading edge of the airfoil. And once I start to get close there, then I switch from my forced transition for my 0.25 case to my natural transition, because the transition is happening ahead of that trip location on the airfoil. Now let's look at the impact on these, because this is the really important piece. Why are we even bothering to do this? Well, first off, you'll notice very little impact on your lift curve slope. It doesn't really have an impact on how the lift is being generated on the airfoil, but it does have a really big impact on the drag polar. So you'll notice in both cases where I've moved this transition point up, so from the natural transition point way far on the aft part of the airfoil, closer up to the leading edge, my drag polar is decidedly worse because it has a higher drag coefficient. And that's because, all things being equal, turbulent boundary layers have a much higher drag coefficient than laminar boundary layers. And that's purely due to the skin friction coefficient value to the velocity gradient that we're seeing near the surface of the flow. So this is why you would like to drive something towards a laminar flow solution. As I mentioned, however, for much larger aircraft, let's think of an airliner which has a very, very large wing and is moving at a pretty good clip, regional, full-scale transport, wide body doesn't really matter. A fighter aircraft which has a smaller chord length on its wing but typically a higher velocity. Those critical Reynolds numbers, if you say, hey, we're in the range of 500,000, that's still going to be really, really close to the leading edge. So you're going to trip the flow anyway. Most of your boundary layer is already going to be turbulent throughout the entire flow. So it doesn't matter. Now, however, at lower Reynolds number cases, in the case of something like a remote control aircraft or a smaller UAV or a sailplane, in these cases, you want to try to maintain this laminar flow as much as possible because that's going to have a really, really big impact on your drag. Okay, and so that kind of covers where we're at with both problem 1 and problem 2. So let's take a look at the friction spreadsheet, and this kind of gives you another tool that you can start using for your aircraft design to be able to predict what the friction drag is going to be. Now, first off, all of this is based upon the friction coefficients that we define in basic fluid mechanics, where you're looking at the value of that friction coefficient modeled by its relationship to the Reynolds number in the flow. So this is looking at that shear layer within the flow, assuming we have a zero slip condition at the surface, and then that is transitioning to a free stream value. So we have our laminar flow solution over here, and so this is the exact solution. And then we have our turbulent flow solution, where we're essentially fitting different types of profiles to that to come up with an estimate. Now, all things being equal, for our skin friction coefficient as a function of the Reynolds number, it's going to be much lower for laminar flow than it is for turbulent flow. And notice these are 2 cases here for the power law fit, and then our Kármán-Schönauer fit in this case. Now, we utilize these then to actually predict what that value of drag coefficient is going to be, basing that on the skin friction coefficient value. Now, in this part of the spreadsheet, which is your working side, first off, notice there's a color coding. The blue cells here are where you can provide input and change your variables. For example, your cruise altitude, your cruise Mach number, and your wing area, and all in standard English units here. And then down here in this range, you have estimates of your wetted area. Now, the definition of your wetted area is any part of that particular component that if you were to dump it in a giant swimming pool, it would come out and get wet. So it's any part of that surface that is exposed to the ambient air. And so you have to make estimates of that total wetted or exposed area for each one of the components on your aircraft. You're doing this for the B2 on this problem. So essentially everything is the fuselage, or everything is the wing. So you can really use either one of those. In this case, it really doesn't matter. You're just breaking these down based upon parts that you can identify on the aircraft. So it sums up the total wetted area, and then you have to provide values for what that Reynolds number is going to be based upon. And for example, in the case of the B2, well, you're varying that Reynolds number from the center line of the aircraft out to the wingtip of the aircraft. So you have to find a mean chord value for that. And then the thickness to chord ratio. From that, then you can calculate what that Reynolds number is going to be, and then you make an estimate of, well, how much of my flow over this particular component is going to be laminar or turbulent. And so in many cases, for something like the fuselage, it's just tripping, right off the bat. It's hitting the nose, it's going over your window. You have all other kind of things, such as airspeed sensors, right up near the front. And so you can assume, yeah, my flow is going to be 0% laminar. The whole thing is going to be turbulent. The wing is a different animal, however, since you're going to have this natural transition on components. And in a high-speed, environment, maybe this is going to be something like 10% or 5% of the entire chord length of the wing where it's going to trip at. Or, let's say we're dealing with something that's much lower speed. I again have something like a sailplane that I'm going to be flying around. So make this a little bit smaller here. And then you can say, well, in this case, maybe I have 75%. Now, this is all just going to be dependent upon those particular values and conditions that you have for that aircraft. Now, what it does then is, based upon this relationship, it makes an estimate using these curves over here on this side and this side to determine what the portion of that is going to be made up by the laminar skin friction drag, and the portion of that is going to be made up by the turbulent skin friction drag. So it's really just a portion in this. In this case, it's 100% turbulent, and then if I change that to 100%, it's going to be 100% laminar. So, I mean, it's relatively straightforward. And then based upon that skin friction coefficient value, which is just within the boundary layer, then you can use our definition of drag coefficient to make an estimate for zero lift drag. And then since you have real values that you've put in here, you can actually make an estimate of that total drag just due to friction drag only. Okay, that should be it. And if we have any other questions, we can discuss that in class.